So before we do some mean inference or population mean inference examples, we're going to talk about the agreement between the confidence interval and the hypothesis test. So if you carry out a hypothesis test and you reject the null hypothesis, then the corresponding confidence interval does not contain the hypothesized value. If you fail to reject the null hypothesis, then the confidence interval does contain the hypothesized value, right? That's what the agreement is. Another thing you have to keep in mind is the values of alpha are not the same, so a lot of times they'll use these subscripts H and C for the alpha for the hypothesis test and the alpha for the confidence interval. So if the hypothesis test is two-sided, they are actually the same as far as the value. However, a one-sided hypothesis test is not the same, right? Because a confidence interval, right? So if it's a confidence interval, let's say it's 90% of confidence interval, right? Let's say it's 90%. Then you have half your alpha here and half your alpha here. So that's 0.05 and 0.05. Okay, that means your confidence interval for the alpha, right, is confidence interval for the alpha for the confidence interval is 10%. However, when you do your hypothesis test, let's say it's a left tail, right? So it's a left tail, then you're going to have, crap, that's not very good. That's not very good at all. All right, let's say you have a known right here, and it's a left tail, and this will be 0.95. So the left tail, this will be shaded here for the hypothesis test, and this will be shaded here for the confidence interval. So this is 0.05. Okay, thus the alpha for the hypothesis test is 0.05. They have to have the same size tails, whatever tail you're doing. So in this case, if the hypothesis test is one-sided, the hypothesis alpha value is half that of the confidence interval, or the confidence interval is twice that of the hypothesis test, depending what the case may be. So if you have a one-sided hypothesis test of 0.05, that means the confidence level alpha is double that at 10, right? Which means it's a 90% confidence, essentially. Okay? If you have a two-sided hypothesis test of 0.05, then the confidence level is the same thing. It's 0.05 also. Okay? No difference, but it's 95% confident. Going the other way, if you have a 95% confident, right? But you want a one-sided hypothesis test, the hypothesis test is only one tail, that means the alpha is only half of that. Again, you can put the subscript if you want. If you have a 90% confidence interval, which means alpha would be 0.05, that's the Stevens level. You have a two-sided hypothesis test, then the alphas are the same for both, right? Oops, I can't seem to copy paste very well. They're the same for both, right? So this is the alpha for the confidence interval. This is the alpha for the hypothesis test. They are the same. Boom, boom. Okay, let's do an example. In the 1980s, it was generally believed that congenital abnormalities affected about 5% of the nation's children. If people believe that the increase in the number of chemicals in the environment has led to an increased incidence of abnormalities, right? So we added plastic and a whole bunch of other stuff to the environment, right? Okay, so we'll do a hypothesis test first. So a recent study examined 384 children, found that 46 of them showed signs of an abnormality. Is this strong enough evidence of that the risk is increased? Do the hypothesis test, confidence intervals, and discuss type 1 and type 2 errors. Okay, so clearly we're looking at a right-tailed test because we want to know if there's an increase, right? So my hypothesis test is a parameter of interest is now is P, which is the portion of children that have the abnormalities. We're doing a Z-test, right, which is the portion of children that have congenital abnormalities. So we want to figure out, is P greater than 0.05, right? Otherwise, it's less than or equal to, right, and it hasn't increased, essentially. Okay, so step 2, we care about random, which we're going to assume they're random, and they're independent, correct? So those are the things that have to be true. So if we do p times q, or n times p, n times q, both of these are more than 10, so we're good there. So it means we have normality. And this is what the population should look like based on the samples, right? So this is actually standard error. Let's put that as standard error, right? Standard error, or the standard deviation of the samples, is this. So it's also less than 10% of the population, so we can assume independence. So we have independence, we have random, we have normality. So we have the 3 checkpoints that actually allow this to happen. Okay, step 3 of the hypothesis test. Okay, so the p-value for the hypothesis test was the 46 out of 384, and the q would be 384 minus 46 out of 384. Okay, the number of values is 384 in the sample. Okay, and this would be the same for the confidence interval. It's the same thing. The difference being is when we do the standard error here, right? This is going to be the square root. What am I doing? Square root of 0.05 times 0.95 divided by the number of samples. Versus the confidence interval is the square root of p times q divided by the number of samples. You're like, wait a minute, why is it different? Well, the hypothesis test is looking at the population, and the confidence interval is using the samples to find the interval, essentially. Okay, so it's not the same standard error for hypothesis test and confidence interval. Okay. Okay, so the z-stat is the sample minus the population divided by the standard error. Okay, so we get 6.275, right? So we need to do 1 minus the normal dot distribution of that value, comma 0, comma 1, comma true. So why 1 minus? Because we're doing a right-tailed test, right? Please draw. If I can get it to draw. Come on, there we go. We're doing a right-tailed test, right? Because we care about being greater than, right? So greater than the value of the 0.05, right? So this is my, we need to go this way because it's a positive z, isn't it? Positive z. Because if I don't do 1 minus, I'm going to get this area in here. So the 1 minus will get me this area over here. Okay, so if I do that, I'm going to get this value right here, right? If I did z critical, it would be normal dot inverse 0.95 comma 0 comma 1, right? And then we get that value there. Okay. Okay. So if we go back to our thing here, step 3. Oh. Okay, so we got 6.275, right? So that's the z value that we got. And we got this right here, which is what, 9 zeros and a 175? And that is clearly a very, very, very small value, essentially, right? And you can prove it that we also need to reject here too, right? So step 4. Is we need to reject this, which should make sense. Okay, so we have this here, we have a shaded area. The shaded area is 0.05, right, which is my alpha for the hypothesis test, right? Okay, and my area over here is much, much, much smaller, right? This is 0.000 dot 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 175, wherever it was, right? Which is this p-value here, correct? Which is much smaller, which means it's in that area essentially, because this is my z asterisk, right? And this is my z stat, correct? That's my z stat. So we did make it into the region, right? Because this is z equals 0 here. Okay, and this was what, 1 point something? What did we get? I think it was like 1.6, whatever it was. So this is 1.6. Right, this is 1.6, whatever it was. This is clearly 6.2. So clearly I'm way over. I've made it way over here to the right, essentially. Okay. All right. So what does this actually mean? So our sample proportion is significant. Right, we made it in the shaded region and not likely to occur. There is enough evidence to reject the null hypothesis. It is likely that the percent of congenital abnormalities is now greater than 5%. Okay? All right. Confidence interval. All right, so do the confidence interval now, right? So the margin of error, we're going to do z alpha 2, correct? So this will be normal dot inverse 0.95 comma 0 comma 1 comma, no, we don't do that. There we go, 1.64, correct? Because again, if we're doing a confidence interval, it's a two-tail. This is a two-tail, unlike the last one, which was one tail, correct? So we have two tails, right? This is z alpha divided by 2. This is the positive one. And this is z alpha divided by 2. This is the negative one, right? So this is plus or minus, right, to get these two values. This is 0.90. You're like, well, wait a minute. This was 9.5 before, wasn't it? Right? Well, yes. If you take one tail and you get 0.05, right, which is the alpha, this is 0.95. But this is a two-tail now because, right, it has two tails. This only had one tail. Okay, so this is a shaded region here. Okay, so from here to here is 95, which is essentially how we got this value here. 0 to here is 95, right? 95, because you have the middle part, which is 90, plus the 5% left tail. So we have the z alpha 2 times the standard error as our margin of error. Okay, so this is the sample minus the margin of error, and this is the sample plus the margin of error. Okay, so their true proportion is in this range, essentially. Okay, so the confidence interval, right, is a 90% confidence interval, and our alpha is 10% essentially, right? Because if we draw this, right, boom, boom, 0.90, 0.05, 0.05. This is our confidence interval in here, correct? And the hypothesis test was a right tail for 0.05, so this is 0.95. So this was the critical region up here. Okay, so this is the alpha for the hypothesis test. This is the alpha for the confidence interval. Two different alphas, right? You can do the little subscripts if you want. You can put a C there and an H there if you want. Doesn't really matter. Okay, so it takes two of these. Got there. All right. So what did I get? 925 and 1470. Is that what I got? Yes. Okay. So what you notice is that the 0.05 is not in the confidence interval. Hence, we rejected. It's not in there, right? So let's talk about the type errors first. Alpha and beta. So the probability to determine the number of congenital abnormalities is more than 5% when it's actually 5%, right? It's a false positive, and the false negative is the true probability to determine the abnormalities is 5% when it's actually more than that. So false negative did not detect. So what does this mean? Since we rejected the null hypothesis, there is a chance of a type 1 error. It is unlikely because the p-value is very, very, very small. And that's an incredibly small p-value. So it's unlikely we have a type 1 error, but it would because we rejected it. Maybe we shouldn't have. That's what a type 1 error is, right? The hypothesis test and the confidence interval are in agreement because we rejected the null hypothesis and the 0.05 was not in the confidence interval, right? So our confidence interval, 0.09 to 0.02, so that's clearly showing that it's higher than 0.05, right? Which would make sense, which is why we rejected this essentially. So we are in agreement essentially. So all of this stuff for inference goes together, confidence interval and null hypothesis. You just have to make sure you select the correct alpha values for confidence interval and null hypothesis. I'm sorry, for the confidence interval and the hypothesis testing, you must choose the correct alpha values such that they correspond. So if they don't specify, okay, a alpha, then use the 0.05 by default for whichever one you do first, whether that's the confidence interval hypothesis test. So the 0.05 default, okay, that's known as the Fisher value, right? So 0.05 by default is the Fisher value, right? Which is the guy who did statistics many hundreds of years ago in the 1700s. So, and that's what people use nowadays by default, unless otherwise specified or calculated. Okay.